Dante is going to talk about the functional replacement in genital locking led to multiple RTA losses in ghost spiders.
Okay, so thank you very much. Thank you very much to everyone for coming here. So today I will present you, my name is Dante. I'm a PhD student at Museo Argentino de Ciencias Naturales. And today I will present you our work entitled Functional Replacement in Genital Locking Led to Multiple RTA Losses in Ghost Spiders. So the retrolateral tibial apophysis, or RTA, is the main synapomorphy of the most diverse group of spiders, which is the RTA clade. It holds around 25,000 species with highly divergent RTA morphologies. But still, the RTA is usually involved in the same, which is the first mechanical engagement between male and female genitalia, which occurs prior to full hematological expansion. And we will refer to this as primary locking from now on, okay? But in spite of this super important function, several lineages lost the RTA, and some Anyphaenidae among them, but still the Anyphaenidae is within the RTA clade. And this raises two basic questions. First, how do these taxa achieve primary locking and overall genital coupling? And then, why was the RTA lost in the first place? So in order to assess these questions, we chose Amaurobioidinae, which is one of the two subfamilies of Anyphaenidae. And it represents really good for assessing this because first, the RTA was lost or reduced in many of its representatives. And then because we now have a robust phylogeny for testing possible evolutionary scenarios that led to such losses. Therefore, the aims of this study were first to study the copulatory mechanics of Amaurobioidinae species lacking an RTA to determine how they achieve primary locking, and then to test possible evolutionary scenarios that led to RTA losses by conducting ancestral state reconstructions. So as for the copulatory mechanics part, we did this by cryofixation of mating pairs and posterior micro-CT scans. Then we virtually reconstructed their genital coupling, and then we complemented this with detailed video footage of the genital coupling as well. And we achieved at least one cryofix mating pairs of 6 species of Amaurobioidines. Okay, this is Amaurobioidinae. 2 of these species are placed within the tribe Amaurobioidinae, and the other 4 are placed within Gasheniinae. So we managed to gather a fair amount of, we managed to cover a fair amount of morphological variability in the whole subfamily. And what we found is that in all studied species, males achieve primary locking by locking their hook-shaped conductor into the ipsilateral copulatory opening. This means that they lock the right conductor is locked in the right copulatory opening, and the conductor holds a double function because it also conducts the embolus through the copulatory opening. And as I was saying, this was really conserved. In all the Amaurobioidine studies, they all have these hook-shaped conductors with really slight, really subtle variations, and they all achieve primary locking in the same way, by locking it in the ipsilateral copulatory opening. The secondary lockings, which are the genital lockings that come after the primary locking, after full expansion occurs, were really variable, both in the structure used and in the mechanisms employed, but we will discuss it later. I included a few clips so you can see how is the main copulatory, the overall copulatory locking, genital locking in Amaurobioidines. They first scrap the female epigynon, then lock the conductor and expand their bulb. This is a species with super short insertions, Sanogasta maculatypes. And therefore, based on the functional data that we just observed, we came to this hypothesis, which is that The primary locking with the conductor relieved the RTA from its function, leading to the loss of it. And I need to say that observations on the genus Acanthoseta were really important for getting to this hypothesis, because the species of this genus still have an RTA. One species still have a fairly large and developed RTA, but they don't use it at all. So this species was really important for thinking this hypothesis, this genus, sorry. The RTA would be around here. It's not coming out in the micro-CT, but it's here. And it's really far away from anything. So they are not using it at all. And as for the phylogenetic mappings, what we did, first we compared between evolutionary models with archaic information criterion and their maximum likelihood. And in order to test our hypothesis, we conducted 3 stochastic mappings. The first one, the first mapping, we coded the conductor as present or absent. And here we can see that the conductor is present in the whole Amaurobioidinae. It's a family, okay? And we can trace its origin back to the A+G clade, which is the base of Amaurobioidinae and Gachenini. So we can say that it's a fairly ancient acquisition of the subfamily. And then we conducted these 2 mappings. Here we coded the RTA as present or absent/vestigial. And we obtained this really interesting pattern where we can count 6 independent losses of the RTA within Amaurobioidinae, which is amazing. 1 here, 2, 3, 4, 5, and 6. 5 of them within the A+G clade. And the third mapping, here we mapped a functional trait, okay? We coded which male structure is used for primary locking, the RTA or the conductor. For outgroups, and we used data from Hoover 1995, which is, he studied Cluvionid and Anyphaenidae. And these blue dots are from this work, it's data from this work. And what they found is really interesting, because we could trace the conductor used for primary locking back to the base of A+G clade as well. So this acquisition here can easily explain these 5 independent losses within A+G clade. This means 5 out of the 6 independent losses, which is great. Therefore, the take-home message would be that both the functional data and the phylogenetic mappings support that a functional replacement in primary locking traceable back to the base of A+G clade led to repeated losses of the RTA. And now going back to the secondary locking mechanisms, unlike primary locking, there were real variables, just mesmerizing variability, and involved many structures. For example, here in Acanthoseta cupicta, males are equipped with this set of teeth in their tegulum, which they use to literally bite this anterior soft area of female epigyne, like in a bear trap mode fashion, like a bear trap. And then Sanogasta have this, male of Sanogasta have this hook-shaped paramedian apophysis, which they used to lock in this medial pouch of the female epigyne. And Aracosia males did something remarkable, because besides locking their paramedian apophysis in the female medial pouch, they also massively expand their distal hematodoca and use it to grab from behind anteriorly the anterior rim of the female epigyne and just pull it really strongly like this. So they grab super strongly to the female. They are super attached. And this was just mesmerizing as well. So we think that this means that secondary lockings have probably less functional constraints. Therefore, they are evolving more freely more freely than the primary lockings. This could be also because the primary the conductor has a double function. It's used for primary locking and for conducting the embolus, so it must contain a high functional constraint, high functional constraints. And then could this mean that there's a strong sexual selection operating over secondary locking mechanisms, given that they are so variable among species? It could. As for the future, thanks. We are working. We are planning to add to the analysis these 5 species. We are either in rearing process or cryofixing or scanning either of them, and we are really interested, especially in Aisha, Hosa, and Negashan. Aisha will allow us to shed some light into the very base of Anyphaenidae. They have a really complex RTA, super complex. We don't know what they use it for. Then Hosa will also shed some light into the base of Amaurobioidinae. They don't have an RTA, but we don't know what they use for primary locking at all. And they reacquire the femoral apophysis. We don't know what they use it for at all. And the other species we're really looking forward to see is Negashan puno. According to mapping, the species should make primary locking with their conductor, and according to morphology as well, but they still have a huge RTA with the hook in its tip, so we don't know what they use it for. So we're really hoping to get some data on this species. We're on the way. So thanks a lot to everyone for listening. Thanks a lot to my awesome collaborators and all my teammates back in the museum. Thanks a lot to the financial support. I couldn't have done anything without their support. So thank you very much to everyone.
Thank you so much. Fantastic talk. We have already a few questions in here lined up. Do any of these species, whoops, do any of these species lack secondary linking altogether?
Sorry, I didn't get that. Secondary locking?
Do any species lack secondary linking altogether?
No, all the studied species have some kind of secondary locking. Yeah.
And next question would be, is the species where the male pulpal structures bite the female in the species, does it cause any damage or irreversibly change the external morphology of the epigyny?
No, I could see that because several of the fixed couples detach, and there was no evident damage into the female cuticle. So I don't think so.
Mm. Do we have another question? Dante, you showed this video with this ultra short copulation. That was in real time?
Yeah. And I think I was super lucky to freeze that species because, yeah, it's in real time. Yeah, it's
wow.
They calculate like that.
So if you're sure that this was really a successful copulation, you may want to follow up with that. That's I suspect that may be the record.
Yeah. I'm working with leucocytes as well, and there's a species that have super short insertions as well. So that things exist, and yeah, I don't know how they manage to do that, but they do. Yeah.
Awesome.